Hi everyone, so I'm just doing a quick video because I've released a couple of updates for the emulator to address some of the problems that were becoming apparent in some of the submissions of the exercises, things that we weren't really aware of and we've hopefully addressed. Now the updates, before I get into them, I did some videos in some past weeks about how to pull updates into the emulator. And so if you look into the emulator here, the commits, you'll see there's two. I've done it the same way again. We've separated into the main, hopefully. Let's just check this. Main demo updates, and then there's the ones for the libraries as well, which you can then cherry pick in. You probably won't need the main ones. So yep, here this is just sort of showing the example, how you would do it in the main, but the one that you're interested in, the one that the only real commit that you need to cherry pick in is this added GL context, blah, 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 right? And so in here, there's a heap of changes to all of the library files. It should just be library files. Let's just double check this. Yes. So the problem that happened, or what I've noticed, now I am by no means a guy who developed graphical applications or has any real deep knowledge of OpenGL. So this is me winging it, but from what I can tell, there was two main issues. One issue was that the TUM draw screen was getting called from threads that didn't own the GL context. Now, if I read through this article here and looking at this sort of thing, there's like current context and they need to be current and one thread can have a context, blah, blah, blah. Now, in our application, we're using an OpenGL, like an SDL renderer. So the SDL renderer is attached to one context, therefore we can only have one thread that at any time is rendering. Now, the calls to TUM draw invokes the renderer to render all of the draw jobs. And so as you can imagine, if you have TUM draw update screen calls from multiple threads, you're going to have invalid OpenGL contexts when this function is getting called, and this leads to crashing. Now, Philip and I realized this months ago, and we created that we bind the context, TUM using TUM bind thread. But now it became apparent to me that some students don't read the documentation as well as they should, because I didn't explicitly make TUM draw update screen check that it's being called from the thread that currently has the context. Now I've done this now, so if you call TUM update screen from a thread that is not the current, that doesn't hold the current OpenGL context, it'll automatically bind the new thread. But now, what the thread binding does, and if we look at libgraphics, TUM draw C, and we'll look at, why it's so slow when bind thread, bind thread, yes, here. Now, if we go through all of this, what it's sort of doing is it's binding the context and creating a renderer, because the renderer is attached to the context. And then, for instance, these loaded images, they're also attached to a renderer. And so since the renderer has to be changed because of the context change, you also have to reload all of your images. And as you can imagine, this has quite a large overhead. And so binding threads should be avoided. Now, this is not to say that I say that you need to update screen from the one thread. I would recommend you to do this, but it's not necessarily required. But you should take into account that there's a large overhead incurred by binding a new thread. So if you're doing a state machine and you're swapping to a different state, as in you're going from the main menu to the gameplay, and you want to just bind the thread once, that's fine because you're only doing this once per 5 minutes of gameplay. But if you're going to bind the thread every frame, this overhead is going to become large and it will make your game unplayable given the slow, given the performance of the emulator on the VM anyway. So I've documented all of this stuff in here, for instance, and I'm saying here there's a large overhead, please don't use this as much as you can. Now, ideally, you should stick to using the same structure as what is in the demo code, because we try and get students to sort of come across this on their own in normal semester, but because of the restrictions or the limitations of the emulator on VMs and on non-native systems, we sort of want to make sure that you don't have problems with this stuff. So generally a good approach and a good performance approach to having to doing games, or at least on embedded systems, on the platforms that we give the students, is that you centralize all of the buffer stuff, meaning different threads draw things to the buffer, and then only one task actually handles the swapping of the memory. And in our case on the emulator, this means that one task actually calls TUM draw update screen, right? Meaning that we don't have to swap the GL context, blah, blah, blah. So you're drawing primitives such as, let's be like some probably here somewhere, like TUM draw field box. You can call this from as many threads as you want because this is thread safe, and it just puts them into a work queue. And then when you call this, the thread that's got the context will actually draw these to the screen, making it thread safe. It's like a bit of a hacky way of getting around the fact that STL and OpenGL context aren't actually thread safe or multi-thread. They're not multi-threaded, right? So if you can stick to this sort of structure of having your TUM draw update screen in one thread at any one time. So you can use this in multiple threads, but you can't do it in multiple at the same time. Because I've changed it now that you'll automatically bind the thread, so you can actually do it, but the overhead will become so large that you'll have massive performance problems. So I found a lot of students were doing update screens here and there. Now update screen essentially should be done once per frame. Like every FPS, every frame, you should call it once. And I found a lot of students when they were blinking their circles, they would draw a circle, update the screen, draw a circle, update the screen. Now, if this happens between 10 milliseconds, I can't actually see the second circle because essentially one of them is getting drawn and the other one's just getting overwritten like straight away, right? Because like it'll be like draw, get overwritten by this one who's cleared the screen and drawn it, and then it waits 10 milliseconds. So I'm only going to be able to see the second one. And so in a few students' submissions, there was a problem that only one of the circles would blink. And this is probably a fact that I'm running a native system, and so like my performance is a lot better. And so on a slower system, you might actually be able to see both of them, but really on a quickly performing system, you can only see one. And so this is a problem of using TUM draw update screen in sort of a non-centralized fashion. Now I've tried to sort of describe this, so please read the documentation. And if you stick to this principle of having sort of one buffer swap task in the background, like you really don't need to change this much. You shouldn't have those problems, right? The second problem, or the second thing that we discovered that was made apparent to us in the exercises, is that the calls to TUM fetch events is not thread safe. And this is because it's on top of, it uses STL get, I think it was called STL fetch events or something. STL poll event here. Now, if we read the documentation for this, somewhere here, and does not suspend, right? And so there's obviously some sort of blocking action happening in the background of the STL because it's not blocking the main, meaning that some sort of background STL thread is blocking. And so the problem that you can have, or that I've experienced from the exercises without having gone into the STL source code, I didn't want to spend time digesting that code, is that you can have, if this call is called from two separate threads at the same time, you sort of end up in a deadlock situation. And so to circumnavigate this problem, I've now made it that you can, in the TUM event library, handling calls to STL poll event is actually made thread safe. So you're never going to double call it before it's returned, sort of thing. Now, also one thing I'm not quite aware of because I'm not STL or OpenGL nut is that I don't also know that STL poll event, because STL is based on OpenGL, that the polling of the events is also linked to context. I don't believe it is because of this article when it's sort of talking about like blah, 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 what is contained to an object, sort of like these objects are shareable, sync objects, container objects, blah, blah, blah. I don't know what all of this stuff is and how it ties into STL, but I'm going to go from the assumption that fetching the events is not context dependent, but it's more of a thread safe issue based purely on the STL threads blocking in the background. Now, to sort of fix this problem, if we go into the events code, so the lib graphics events, Now I have put in a check here to say, ideally call it from the context, the thread that holds the context, because then we're guaranteed that we're safe and we don't have this problem, because if we don't know 100% sure. But if you call it from the thread that holds the OpenGL context, nothing bad's going to happen. Ideally, we won't get any errors, but this might not be the case. But so you can skip this check, and I'll get this to in a second. But essentially, I've modified TUM fetch events such that it takes in a bitmap of flags. Now, if you don't know how flags are passed to functions in C commonly, usually people use like a bitmap. You have I want to be able to call in to pass in 3 or 4 separate flags or not pass them in. And so the easiest way is that you have a byte that represents 8 flags, and if the flag is to be set, it'll just set that one bit, and you just go through and check which bits are set, as you can imagine, and it'll say, yep, okay, this bit was set, it means this flag was passed in. And so I've documented it here that the TUM fetch events has 3 flags that can be sent in. So you have the event fetching flags, and it's these 3. So you can either block or non-block. Now you can pass them both in at once, but it'll block. Blocking takes preference to non-blocking because blocking is checked first. So, and the default behavior is also non-blocking. So you actually don't need to pass in non-block, but just for, completion, for sort of human readability, still pass in event fetch non-block. So you can either have a blocking functionality or non-blocking. Now you don't put in a delay, it's literally just it blocks until it returns, or it tries it. If it doesn't work, it keeps running. It just continue without getting a result. And so this is the 2 actions here. And now there's also this fetch event no GL check. And so what that is simply in the beginning of the function here, I have this sort of to check that the thread that's calling it is the current GL thread, context thread. And if you pass in the flag fetch no GL check, it just skips this, meaning that you can call this function from threads that don't hold the OpenGL context, which is probably what you're going to want to do most of the time if you want to get fetch events from different threads. And so this is sort of explained here, and this is how you would then pass in multiple flags at once. You just OR them together, because you can imagine that non-blocking is the second bit, no GL check's the third bit, and so you just OR them, and therefore you're sending in 1, 1, 0. And so this just sends in, and then in here, I'm just doing some sort of bitwise checking and seeing what flags have been set, and then I handle the whatever appropriately, right? So read this documentation, it should be quite straightforward. Now, I have also included updates or changes into the main documentation that sort of exemplify this. So in the swapper task here, I'm doing a fetch events blocking. And then I also have another call here, another blocking call here. This could be non-blocking if you wanted, it's totally up to you. But this one here, since we have in the, this is our swapping task, and this has been TUM bind thread, so this is the context thread. So here, if we call fetch events without skipping, it's not going to throw us errors, because if you call TUM fetch events from a thread that doesn't hold the context and you don't pass in the flag fetch, skip the check, it will just spam you errors, because if we look here, it just prints an error, and so you can imagine every frame you'll get this error spat out at you, and it's just going to be and this is sort of just to say for you to be aware that you've done this. This is why the error is there. So it makes it very obvious that somewhere in your code, you're calling it from a thread that doesn't hold the context, and you haven't told it to skip. You haven't explicitly told it to skip. So exactly here. So this guy is is skipping the GL check and is calling it from a different thread. Now for me on my system, this runs, this is stable. So this is one reason I also don't believe that the getting the events is bound to the GL context, but I've put it in anyway, because you can be better safe than sorry. Now, so these are the 2 big changes that have happened. So just to reiterate, please make sure that you use a swap buffers sort of structure where you have one task that runs in the background that is bound to your GL context, and it handles TUM draw update screen. Now, please don't put this in multiple threads, otherwise you're going to get problems. Now, you can call any of the TUM draw methods like, clear screen, draw triangle, draw box, draw string, draw text. These are all thread safe. And it's only really just this TUM draw update screen. This is it. This is the one that's the problem. and then you can do this fetch event from anywhere in your code, but now you're going to have to pass in the block or non-block flag. You don't actually have to pass in non-block, that's the default, but just so if you were to just call TUM fetch events brackets with nothing in it, it would be a non-blocking call to TUM fetch events, but if it's not the thread with the GL context, it will throw errors at you. Now, hopefully this helps or clears things up. Now, in going into the project, if there are students that are sort of not following this, I'll also sort of know that they didn't watch the video, because it would be really handy if people could stick to this one, mainly just this TUM draw update screen, because this is going to sort of get rid of a lot of the incompatibility issues between, you know, your system, my system, based on like hardware, whatever. Now, I'm going to do one more tutorial hopefully this afternoon where I go through the asynchronous I/O library, because in the project you're going to need to doing like sort of, you know, communications, and this is because in normal semester students will have a working groups of 2, and they'll use UART to send information between the 2 boards, and they'll do multiplayer sort of stuff. Now, this semester, seeing as you're doing everything by yourselves and we're not actually using embedded systems, we want to sort of do the same thing. We actually have to sort of handle in the background some sort of communications. And so what we've done, or what we're going to be doing, which I've sort of described in the PDF, is that we'll have some sort of pre-compiled binary that will distribute to you guys, and then it will handle replying, or it'll take in your information and it will reply certain values to you that you can then handle. And you'll need to do this through the asynchronous I/O library, which is built upon POSIX message queues, but namely we'll be using POSIX sockets. Now, to quickly, before I go into that, now it obviously exposes TCP sockets and UDP sockets. Now, for those of you that don't know the difference between TCP and UDP, I would have a quick Google and read up on it, because it's going to come up in the rest of your, essentially, the rest of your engineering careers. If you're doing anything relating with computers that send information on a network, you're going to need to know the difference between TCP and UDP. Now, like a really 2-second sort of summary of the difference is that TCP, they have sequences. So like if you have a packet, like if you want to send 10 packets, each packet has a number, and the TCP protocol makes sure that these packets are all received in the correct order. So if a packet is somehow lost in the network, it will say, hey, I didn't get packet 3, and it will resend packet 3. So TCP guarantees delivery, but it also has a very high overhead in it. So as you can imagine, if I'm sending you 10 packets from here to like China, and I'm on some super sketchy network, packets will get dropped and lost. It can take a while for these packets to be retransmitted, but essentially you're ideally guaranteeing that all of your packets get there. And UDP, what it is it just spams whatever it is to the receiving address. There's no conflict, there's no sequence or anything like this. There's no guaranteeing that your data arrived. But as you can imagine, TCP is good for like sort of non-time critical, where you want to guarantee data integrity, like, you know, the whole packet. UDP is sort of really good for real time, because it's just streaming, it's just spamming the values out. So if you want to send your player's location, you don't need to guarantee that the opponent received the last position, because he only really cares about the current position. So you're just spamming him the current position. If a packet gets dropped, that's just how life is. You're just going to get the next packet, and then he'll have to adjust to that packet. So we'll be pretty much we'll be focusing on UDP for this reason. But read up into TCP and UDP. The protocols are obviously a lot more complex than what I just explained them, and they're definitely something that is worthwhile for getting a decent understanding of them. I as well am not a networks guy, but I have enough of an understanding that when someone talks to me about the different, like wants to create I'm like, hey, I want to use a TCP socket, I have a bit of an idea of like what's going on. And this is useful. You don't need to know in detail, just have a basic knowledge. And also some of the students were saying that these tutorials or sort of demos, code breakdowns help them, which I'm really happy about. I mean, that means a lot. But if there's any sort of other topics that you want me to sort of talk about or discuss, do some code, whatever, just let me know. Send me a message in the chat, in the Rocket chat, and I'll see if I can find time to make some more demos or whatever, something to help you guys out, because I think it's really good. I wish that I had someone explaining these things to me like 5 years ago. And so, yeah, I hope this all helps, and please read the documentation. Documentation is sacred. So thank you, and I'll hopefully see you later this afternoon for the asynchronous I/O one. Thanks.